The good ship Dirac. Exploring Maxwell's equation has filled in some of the physics behind the QED, and it built a road network for us that bridges atoms land and the electron, atom land to the electron. It will allow us to travel through the interior of the islands we discover on our voyages. It has also brought Einstein's relativity into view. But Maxwell's equations are not quantum mechanical, but we already know that without quantum mechanics, atom land makes no sense. There is a huge and unexpected reward to be had by looking at how relativity and quantum mechanics come together in QED. We've seen the wave-like nature of the electrons around atoms, which is an essential feature of the chemistry. And physics, yes. This wave-like behavior has to be generated by some kind of wave equation, because that's how waves work. The simplest equation that can be used to do this was derived by Erwin Schrödinger in 1925. It takes a classical relationship between the energy of particle and its momentum. The energy is equal to the square of the momentum divided by twice the mass, E equal p square over 2m, which is equivalent to the possibly more familiar expression for kinetic energy, E equal 1/2 mv square, where the v is the velocity. Yes. And by some ingenious sleight of the hand makes a wave equation out of it. The way this is done is to redefine the energy and momentum of the particle as being properties of the underlying quantum state, a new kind of underlying object that contains all possible information about the particle. This energy is related to how the state changes with respect to time, and momentum with how it changes with respect to distance. But this is no longer good enough. We need to take relativity on board. It is a little as though we have an excellent little boat for chugging around the coastline of our islands, hugging the shore of atom lands. But we need something more powerful and heavy duty to take us further. We need a bigger boat. That's where the Dirac equation comes in. The classical pre-relativity relationship between energy and motion dates back to the Isaac Newton and others in the 17th century. It states that the kinetic energy, the energy of motion, is 1/2 times the mass times the square of the speed. After Schrödinger's trick, this becomes a wave equation which tells us how quantum particle moves. Wow, that equation works very well in predicting the behavior of the electrons and other particles, including many subtle quantum effects. For example, with the energy levels of the electrons around the atom that we already explored. But the energy and momentum relationship we started with is only valid at the speed much smaller than the speed of the light. It does not incorporate the lessons of the relativity. So as we explore the behavior of particles at higher energies and higher speeds, we need to improve the Schrödinger equation to take into account the relativistic effects. Sure. Taking a similar recipe to that used by Schrödinger to obtain his wave equation, the obvious thing is to use Einstein's new relation between energy and momentum and make the same replacements. That is, the energy tells us about the time dependence of the quantum states. The momentum tells us about the dependence on the position, and we should get a new wave equation that works even at speed close to the speed of light. The complete form of the Einstein's E equal mc square includes the momentum of the particle as well as its energy and mass, and relates the square of the energy to the square of the mass and the square of the momentum. If you want to know, the full expression is E square equal m square, the force power, c to the force power plus p square times c square, where E is the energy, m is the mass, and p is the momentum. For zero momentum, this reduces to the E square equal m square c to the force power to the force power, and taking the square root of the both sides gets us as the familiar E equal mc square, and possibly E equal minus mc square too. And that presents a problem when we try to turn it into the quantum wave equation. Equations involving squares generally have two solutions. Yes. Equation involving squares generally have two solutions. If I know that the square of some number is 4, what do I know about the number? I might be 2. Since the square of 2 times 2 is 4, but it could also be a minus 2, since minus 2 times minus 2 is also 4. Likewise, minus e multiplied by minus e is the same as e multiplied by e. It would seem that our new equation allows navigate energy particles. Wow. This is not an easy thing to make sense of. What is particle with a negative energy or even negative mass? This turns out to be quite an important question. Remember that to get the right answer about quantum particles, how they move, where they go, how they interact or bind together, we have to include all the possibilities for how they might move and where they might end up. Only then do we get the proper mix of the wave-like and particle-like behavior that is seen in nature. This means we cannot pick and choose a solution to our wave equation. All possible solutions have to be taken into account, and that means we have to allow electron to have negative energy. Lots of it. Wow. So yeah, that is my position, right? Yes. So all possible solutions have to be taken into account, and that means we would have to allow electrons to have a negative energy, lots of it, and we don't see those electrons around in nature. Worse, those negative energy states would allow positive energy electron to sort of sink into them, make it move into the bottom, right? Sink into them and vanish. The number of electrons would not be conserved. Whoa. Very bad news for conservation of electric charge and totally incompatible with Maxwell's equations. None of this matches the way electrons actually behave. So, at least for the electrons, the default recipe for making a quantum wave equation fails. We do indeed need a bigger board, in other words, bigger picture, right? The negative solutions are allowed it because the energy is squared in the equation. So the negative solutions are allowed it because the energy is squared in the equation. What is really needed is the equation where the energy appears only once, not squared. Wow. This is true in the Schrödinger's equation, but because of the way relativity mixes up energy and momentum and space and time, the momentum must appear to the same power as the energy. In the Schrödinger equation, the momentum appears squared, which will not do. Wow. So, to summarize the problem, to carry us any further in understanding particles, we need an equation which is consistent with relativity, but in which the energy and momentum are not squared, something like energy is equal to A times the mass plus B times the energy, where A and B are some unknown numbers we need to work out. This is kind of the things we do in mathematics very often. Yes! find A and B, and we are on the way. Yes. Sure. The problem is there are no numbers that work if we substitute them for A and B. To make the equation work, you need A and B to be objects that don't commute. This doesn't mean that A and B work from home or live over the shop. Commuting in this context means that A times B is the same thing as B times A. Wow, it's such a basic mathematical rule. That's true for all numbers. The multiplication tables learned at school all show commutation. In that if we know that 5 times 6 is 30, we know that 6 times 5 times also 30. Even imaginary numbers are such as the square root of the -1, which you might think would be weird enough to do just about anything, commute and therefore don't help us towards the relativistic wave equation we need. You don't need to understand exactly how this works in order to continue our exploration, but if you'd like to see it, here goes. We want an equation like E equal AM plus BP, but which is also consistent with E square equal M square times C the fourth power plus P square times C square. If we square the first equation, we have to multiply all the terms by each other, so we get E square equal A square times M square plus bracket AM times BP bracket plus bracket BP times AM bracket plus B square P square. Now we have two expressions which ought to both equal E square, so they must equal each other. M square times C fourth power plus P square times C square must equal A square times M square plus bracket AM times BP plus bracket BP times AM plus B square times P square. For any values of the M and P, yes. If we let A square and B square both equal to the C square, that takes care of the terms involving the square of the mass and the square of the energy. But we are left with the other bit, bracket AM times BP plus bracket BP times AM. This can only be 0 for all values of the P and M because we want an equation which works for all particles. If A times B is equal to the negative of the B times A, but for all numbers A times B equals B times A, so A and B cannot be numbers. At this point, it might be tempting to give up and leave the rest of the map blank. Maybe the behavior of the subatomic particle is just not susceptible to the mathematics. Perhaps there is no wave equation that can properly describe electrons and at the same time agree with relativity. Maybe these waters are too rough for us and the laws too difficult to pass. Not for Paul Dirac. He met the challenge to find an equation that describes the motion of the quantum particle moving at a relativistic speed in 1928. It involved a strange form of the mathematics not used so far in this exploration, but luckily waiting there in our toolkit to be used. Wow! The important first step is to note that there are mathematical objects that do not commute. One such type of the object is called a matrix. In mathematics, a matrix is an array of the number arranged in the rows and columns, governed by the rules dictating how they should be multiplied together, and so on. Yes. From the point of view of the mathematics, the number can be pretty much anything you like, although if we want to use them to help us understand physics, they take on specific meaning. For example, the number in the matrix can encode how the different components of the magnetic fields change when we rotate it through some angle about some direction. Wow! Mathematics do this quite a lot, defining some new abstract mathematical object with some specified behavior and then playing around to see what the consequences are. Yes, mathematics! From the point of view of the mathematics, it matters not at all whether there is any correspondence between the new toy and the physical world. But from the point of view of the physicists looking for some things that don't commute, to help make more sense of the map of the physics, it can be the treasure trove. Yes. Matrices can slot in there instead of a number in the trial relativistic wave equation we are trying to build. They make it work, and then the mathematics of the matrices can help us see what the physical predictions of the equation might be. In the Dirac case, they are dramatic. The simplest matrices that can make the Dirac equation work are arranged in a 4-column and 4 rows of the 4 numbers each. These multiply the quantum field describing a particle just like the terms in the Schrödinger equation. But the rule of the matrix game means that the objects they multiply can also no longer be simply numbers. They have to have 4 complex components arranged in a little column. Once you have decided you need matrices, you need 4 quantum fields to describe a particle, not just one. Wow! As one might expect, the fact that there are 4 components to the quantum field has real physical consequences. This will allow us to travel into deep south and also explain one of the mysteries we encountered long ago, back in Atom Land. Thank you.